We're starting a new subject today. Well, it's related to what we have seen at the beginning of this semester. So back to entropy. So entropy and probability. Right. So if you remember, for the microcanonical ensemble, we had this expression, sk log of the number of states that we have. Okay. Now we waved our hands a little bit about this expression and said, well, yeah, the number of states or the log of number of states grows linearly, entropy grows linearly. So this is why there is this connection between the entropy and the log of the number of states. Now this equation, first of also known as the Boltzmann entropy, and it appeared in the works of Ludwig Boltzmann something like 150 years ago. His argument was somewhat different from what we have said, so let's try and repeat the Boltzmann argument for the entropy as it's expressed over here, and then we'll try to generalize it for different systems. Okay? Now, why we cannot use this expression for entropy, for example, for the canonical ensemble? Now, this quick answer is that all the different states that are accessible in microcanonical ensemble, they have exactly the same probability. Now, in the canonical ensemble, the different states have already different probabilities. Why? Because different states usually have different energies that we have different probabilities, and here it's just the number of states, and somehow those different probabilities of different states should enter the entropy and affect it. Okay? So if we just use the number of states for the system where different states have different probabilities, it doesn't sound right. Okay. So let's start and see where this guy appeared from, and let's try and generalize it for canonical ensemble. Okay, so how Boltzmann got this equation? Of course, he knew something about gases, and he knew something about the basic law of thermodynamics. So he used this equation, P equals TdS minus PdV. Okay, remember the second law of thermodynamics that connects equilibrium states of any system, basically. Great. Now, we also want to use the ideal gas equation. Okay. And we want to use the fact that we are going to perform some isothermal process. So Boltzmann argument goes like this. So if I have molecules inside a chamber, okay, and the volume of this chamber is V1, while the total volume is V2. Now, let's assume that I puncture this membrane and I now let the particles expand from the smaller chamber to the larger chamber. Okay, so what will happen? So how can I relate the different properties of the system before and after? So what I'm saying before and after, so before in equilibrium, after also in equilibrium. Why in equilibrium? Because this equation over here relates equilibrium states to other equilibrium states. Okay, so I'm going to use this equation, and this is a crucial point, I assume that the expansion happened at constant temperature. Somehow I managed, okay, to keep the temperature constant. So what's going on? So first of all, yes?
How do you define temperature not in equilibrium?
How I define, so I define it for equilibrium state number 1, and then for equilibrium state number 2 I can define temperature.
So it's not defined for
Why? Temperature is always ds to du equals 1 over t.
But what is S in the middle of it?
Not in the middle. I don't care what about it. So in the middle, I can say I expanded a little bit, not to the whole chamber, but to the part chamber. It's all those stories about quasi static process, etc., etc. Okay. You don't really care if you work on the initial state and the final state. What happens in between? You don't care, okay? Because this equation still holds for the initial equilibrium and final equilibrium. Okay. So what happens if we keep the temperature constant and we want somehow to relate what happens to the entropy at the initial state and at the final state? Okay, so the topic is entropy, so I need to somehow relate the entropy before and after. Okay, so from this equation I know that ds equals 1 over t du minus p divided by t dv. All right. Now I also know that du equals cv dt. Okay. Why? Because cv equals du to dt. So I'm going to use this. Plus. Yes. Of course. If it's minus over here, it has to be plus over there. So we have cv equals du equals cv dt. So we have here ds equals 1 over t. Here we have cv dt plus p divided by t dv. Okay, now because it's isothermal process, I don't really care about this term because dt is 0. So this guy is going away. Now, here, instead of using P, I'm going to use P equals to RT divided by V. Okay. So what we have here is ds equals to RT divided by V multiplied by 1 over T dV. So ds is R1V dV. Now, this is already a simple equation, and I can say that if I perform an integration from the initial state till the final state, I obtain that S at the final state minus S at the initial state equals to R log of the final state minus R log of the initial state. And basically I can say that S2 minus S1 equals to R log of V2 divided by V1. Okay. Great. So this is the thermodynamical representation of the difference between the entropies when I let my gas expand. Okay. Now, so this is this part. Okay. Now Boltzmann somehow wanted to relate entropy to the probability, okay, which is a genius idea. So now we're going to see how the entropy is related to probability. Now it's really hard to say how entropy is related to probability because we don't really have intuition about entropy, right? So we know what energy is. The energy is the possibility to perform some work, potential energy. Entropy is So what is that? We know that entropy grows with energy, the entropy is maximal, but we don't really have any intuition about entropy. So if we really want to say something about entropy, entropy is, if we already have an energy, is how much of this energy can actually be used. This is the notion of entropy. Now, we don't know how to relate S's to probability, but Boltzmann thought about this problem in different perspective. He said, I don't know what S2 and S1, but I know somehow about the V2 and V1. Those can be described in terms of probabilities. Okay, so what he have done? He said the following thing. Let's assume that I have one particle. Right. This particle is, take one of them. Okay. It doesn't really matter who I take because the gas is identical and everybody are exactly the same. So I take one particle. And I ask myself, right, so what is the probability of this particle to be somewhere inside this chamber of V1? So I have to count the number of ways where I can put my particle inside this chamber, okay? And this number of waves is going to be related, okay, to the probability of this particle being inside the chamber. So let's say that W is the number of different ways that I can put my particle inside this chamber of volume 1. So this is W1. Now, the number of different positions have to be proportional to the volume V1. Okay. The proportionality constant, it doesn't really important. Okay. So we say that the number of ways that we have to put, or we can put this particle inside the chamber V1 is simply V1. Now, the number of ways that we can put two particles inside this chamber V1 is what? It's the number, because they have no interactions, they don't care about each other, okay? So it's like independent random variables. So the number of ways that we can put two particles is V1 squared. Put it over here, 1 and 2. Okay. Now if I have, instead of 2 particles, I have 3 particles, 5 particles, 8 particles, if I have n particles, so the number of different ways that I can put all those particles inside this chamber V1 is the number of ways for the first particle multiplied by the number of ways for the second particle, multiplied by the number of ways for the third particles, etc., etc., etc. So Wn is d1 to the power n. Okay. Now, look on this equation over here. What do I have? So instead of writing down with V2 and V1, I'm going to use the following description. For n particles, okay, log V to the power of n equals to what? To n log of W. Oh, I'm sorry. N log of V1 equals to log of W. Okay. And let's call it W1. So it's the number of ways to put n particles inside a chamber of volume V1. And n log of V2 equals to log of W2. The number of ways that I can put n particles inside the chamber N2. Okay, so we can now go back to this equation and what we see. Yes?
Do you consider Gibbs paradox? It is divided by n,
Gibbs arrived later, and Boltzmann had no idea about his paradox, and I don't really need it right now. Okay. Now, what will happen? Of course, the solution, we know that you have to divide everything by n factorial. But let's look on those guys. let's look on those guys. So we have S2 minus S1 equals to R log of V2 minus R log of V1. Now, log of V1 is 1 over n log of W1, and log of V2 is 1 over n log over W2. So S2 minus S1 equals to R divided by n of log of W2 minus R divided by n of log of W1. So now, for this equation, we already have no volumes, no nothing. So entropy, number of states. Now, what is R divided by n? It's just K Boltzmann. Right? So the Boltzmann constant is this ideal gas constant divided by the number of particles that we have. Okay. So look what we have. S2 minus S1 equals to K Boltzmann log of W2 minus K Boltzmann log of W1. So Boltzmann said the following thing. The entropy, any entropy, at least for ideal gas and stuff that behaves as an ideal gas, equals to log K Boltzmann log of W. What is W? The number of different arrangements of my system. I'm taking my system, I'm looking on all the different rearrangements that I can actually come up with in order to describe the system. I take a log of this number, I multiply it by K Boltzmann, and I have my entropy. Remember, okay, what we had, the original, was that S equals to K Boltzmann log of omega. Okay? So we had a hand-waving argument. Now it's already not a hand-waving argument, but it's something about the ideal gas properties. And even more than that, we can simply say, well, it's even not about ideal gas, it's about the number of different arrangements that we have for our system. Okay. By the way, this equation is engraved on Boltzmann tombstone, and this is the starting point for what entropy is. Right? So we do see here already not a macroscopic idea of entropy that enters the equation of du equals TdS minus PdV. If you remember how we started the description of entropy, entropy is something that grows with energy, and we also deduced that the something has to be maximal. Okay? Now, based on the ideas of Boltzmann, we know that it's related to the number of states inside the system. Okay, so this is at least explains our hand-waving arguments that we had previously in this class. But my question was, well, we assume this formula and use this formula for the microcanonical ensemble. Now, for for canonical ensemble, this might be not true. Why it could not be true? Well, because the energy is not constant, so the different rearrangements have different possibilities. If they have different probabilities, this assumption that the number of different rearrangements equals to V1 is already not true. Okay, so we need to somehow generalize this idea of entropy is K Boltzmann log the number of states to a more general statement. So first of all, let me try and write down this not as a function of number of waves or number of rearrangements, but actually in terms of probabilities. Okay. Now, the probability of being in any state I, when all the states are equally probable, okay, is what? Is just 1 over omega. So all the states are equally probable. So if I want to write down the entropy in terms of log, not log of omega or log of W, but actually in terms of probabilities. So S equals K Boltzmann log of 1 over Fi. Right. And I just write it down as minus K Boltzmann log of Fi. Now, this is somewhat strange way to write it down. Why? Because, well, why specific I over here? Right? You can say, well, Stas, it doesn't really matter because all the i's are exactly the same. Now, I can say if all the i's exactly it's the same, let us write it down slightly different. Okay. So I can say if all of those are exactly the same, I can say that S equals minus K Boltzmann. I want to sum over all the different states, and in 5 minutes you will understand why. I want to sum over all the different states, and here I'm going to have Fi log over Fi. Okay? Why true? Because log of Fi equals to what? Of minus log of W. Okay? So if I put it over here, I have S equals to minus K Boltzmann sum over Fi log of W, and we're going to have a minus over here. I can take log of W out of the summation. Let's put it over here. I'm saying the following. So it is minus K Boltzmann, a sum over I, Fi minus of log of W. It equals to plus K Boltzmann log of W. I have here a sum of I, Fi. And the summation of all the different probabilities have to give me always 1. So I obtain that S equals to K Boltzmann log of W. So it holds true, then even for microcanonical ensemble, I can write down my entropy as minus K Boltzmann sum over I Fi log of Fi. Okay. You can say, Stas, it's a very nasty way to write down this nice formula. Okay? But actually, this is the general way to write this formula. We will see in a second why it is so. Okay, so although we have used only this expression, because we have defined properly the entropy only for the microcanonical ensemble, the true formula is this one. Okay. So let's see if it's indeed true. How I'm going to see if it's indeed true? I'm going to prove that the same formula holds not only for the microcanonical ensemble, but also for canonical ensemble. Okay. So this is microcanonical ensemble. What happened for canonical ensemble? What do we know, or how we can relate the microscopical behavior, the probabilities of different microscopical states, and the entropy? Okay. So what do we know? We know the following thing. First of all, we know always that F equals U minus Ts. Okay. So here we have the entropy in this equation. This you can say, well, Stas, very nice, but this is a thermodynamical equation, and how it relates to microscopical relation. Well, first of all, U is sum over I, Fi, Ei. Okay. I don't have to describe it in terms of U. U, and we have proven this, U is the average energy of the system. And the average energy of the system simply defined by the sum of the probability multiplied by the value of the energy for this specific state. Sum over all states. Okay. Great. So we have this term in terms of some microscopical properties. What about F? F we also know. Right? So what is the expression for F when we use only microscopical properties? It's minus 1 over beta log of z, where z is sum over I, E minus beta EI. Great. Okay, so if we plug this inside and this inside, okay, we might have some sort of description of the entropy. Okay. So what we have 1 minus beta, 1 over beta, log of z equals to sum over I, Fi, Ei, minus Ts. So it's easy to extract S out of this equation. It's simply S equals to 1 over T, sum over I, Fi, Ei, and we have plus 1 over beta, right, log of z.
Beta t.
Beta t. Thanks. Yeah. Seems reasonable.
What are you trying to do here?
I'm trying to tell you what is the expression for entropy for the canonical ensemble. So this is canonical ensemble. This is the expression for entropy for the microcanonical ensemble based on Boltzmann and waving arguments about ideal gas. Now we have, or we try and obtain an equation for S for the canonical ensemble. Canonical ensemble. Alright, so this is the question. What is S? Now, of course we can say S is F minus U divided by minus 1 over T, divided by minus T. But it's not enough. We want to describe the entropy in terms of the probabilities, as we did for microcanonical ensemble. Alright, so we already have a nice expression. Right? So we have EI, we have Z, but I don't really like it. Why don't you like it? Because I want a nice formula like this one, which depends only on the probabilities. Because entropy tells me something not about the energies, but about the disorder, about the spread of the system among its possible states. Okay. So in microcanonical description, all the states are exactly equally probable. Okay. So the system spreads uniformly among all of its states. Somehow maybe different might happen, it can happen for the canonical ensemble. So let's see, and I don't want an expression that depends on EI. I want something clearer that only depends on the probabilities, not about the energies. Okay. Now, I expect a universal behavior, so I expect to see something that looks like this. Now, in order to see this, let's do the following trick. So first of all, we have here, instead of T, beta is 1 over K Boltzmann T, right? So we have 1 over K Boltzmann. So here it's K Boltzmann, log of Z. This guy. Here we have 1 over T, sum over I, EI multiplied by Fi, and I want to multiply this by K Boltzmann and divide it by K Boltzmann. Why? Because I have a K Boltzmann over here. Okay. The next term, let's take the K Boltzmann out. And not just the K Boltzmann. I want to write down as a minus K Boltzmann. And inside here, I have sum over I, Fi, minus beta EI, minus log of Z. So I have taken one minus out. Okay, so here it's another minus, and here it's another minus. Okay. The next step is, here I have a summation over sigma over all the different i's. Here I don't have any summation over all the different i's. So, but it's easy to introduce another summation over all the different i's, because sum over I Fi equals to 1. So I can write it down as minus k Boltzmann sigma of I Fi minus beta Ei minus summation over Fi log of z. So I basically multiplied log of z by 1. But it assists in the following thing. I can now sum over different Fi's and look on the log of z and minus beta Ei. Now moreover, because I have a logarithm over here, I want to write it down also as a logarithm. So I have minus k Boltzmann sum over I Fi log of e to the power minus beta Ei. Here I have plus sum over I Fi minus log of z. Okay. Now I can take this sigma over I Fi as a basically take it out of the parenthesis and say that I have minus k Boltzmann sum over I Fi, and inside I have log of e to the power minus beta Ei minus log of z. We have minus k Boltzmann, we're almost done, sum over I Fi, here we have log of e to the power minus beta Ei divided by z. What is this guy inside the parenthesis? Fi. So we have minus k Boltzmann sum over I Fi log over Fi. So you see, this is we obtained for microcanonical ensemble. We also obtained that S equals minus k Boltzmann sum over I Fi log of Fi for the canonical ensemble. Now what's the next step of the physicist, or that he says exactly the same formula that appears for two very different settings? Okay, so what's the assumption? It's true for everything, right? So this is the next assumption. What is entropy? This is entropy. How you define entropy? This is how I define entropy. Okay. Now, it holds for all the different canonical examples that we have seen, all the microcanonical ensembles that we've seen, and it's not a really questionable step forward to say this is how I define entropy. Now, later on in 1948, Shannon defined this as an information entropy, and he had all the different mathematical requirements, what is disorder and what is entropy and what entropy has to be satisfy, and he proved that this is the entropy. You know, he had a very specific set of requirements that was based on this formula, and he proved that this formula is fine. But this is actually why we think it's entropy and why we use it. It comes from the two observations. It holds for microcanonical and canonical ensemble. Even more, we can define different ensembles, like grand canonical or other ensembles, and even for those other ensembles, the same formula will hold true. Okay? So it's not just two ensembles, it's basically any ensemble that you physically can think of. For all of them, the same formula for the entropy will appear. So now at least we have a mathematical description based on microscopical states and microscopical probabilities of what is entropy. It doesn't really improve our intuition much, okay? But at least we have a very clear microscopical formula. So again, if you trying to think about entropy intuitively, the way to think about it, it's like if you have an energy, the amount of energy is how much work you can produce out of it, or force you can produce out of it. Entropy, in some sense, says, well, how the system spreads, and if it spreads too much among all over its possible states, you cannot use the energy. But if it's concentrated and the entropy is really, really low, you can always use the energy. So the entropy is a description of amount of usable energy that you can actually, that you have inside your system. Okay? So it's always something about energy. The entropy is just says about how the different states are spread, so how many usable energy that you have inside your hands, or inside your system. Great, so this is our entropy. And the next thing to do is, well, if we have entropy for any ensemble, we also have a maximal entropy principle, right? Remember this maximal entropy principle? Maximal entropy principle. What is the maximal entropy principle? In equilibrium, the entropy for constant energy has to attain a maximal value. Now, this is the question of the chicken or the egg. So you can say we used a lot of different thermodynamical laws in order to derive this those expressions and this principle. Can we turn the wheel around? Can we say, well, actually, it's not all those empirical thermodynamical laws that define everything, but this principle and this form of entropy, this is what actually defines everything. So this idea comes from analytical mechanics. What we have in analytical mechanics, we have Newton laws. Based on Newton laws, we define that there has to be a Fermat principle, that there is an action, and we have to find the action, and it holds, and then we say, well, Newton laws are not important. The action and the Hamilton principle of maximal action, this is what's important. The same happens here. We work really, really hard in order to derive this form of entropy and this maximal entropy principle. But what we can say now, and I will prove it to you, that we don't need anything else but just this form and this principle. All the other portions of this class, or at least what are the different probabilities, what are the different thermodynamical laws, are based on those two assumptions. Everything else is derived from those two guys. Okay. So let's see how it actually works. I want to prove it to you and not just say, well, I have now something. Okay. So if you were a mathematician, part of you are, so you could say, well, this is the starting point and I don't care about the thermodynamical laws. This is the form, this is my Hamiltonian, this is my action, this is my maximal entropy principle, and this is all I need. I don't need to understand or know anything else. I can derive everything from scratch each time I need it. Okay, so the question that I want to prove is how to obtain the probabilities Fi based on the form of entropy and the maximal entropy principle. How actually I obtain different values of different Fi's if the only thing that I know are those two guys. So what I have told you is that we need to take this guy. In order to find the maximal, we have to take the derivative of it with respect to all the different Fi's and find the maximal. So maximal with respect to what? The different probabilities. Okay. So we need to solve the following equation. Delta S, the variation or the derivative of S, the entropy, have to be equal 0. Okay. So what is this delta over minus k Boltzmann sum over I fi log over fi is just the differences, small differences. It's called a variation. Exactly as the variation goes for the analytical mechanics. So we have minus k Boltzmann delta over sigma over I fi log over fi. Now, so this is the variation or the difference of a sum. We can basically take this and put it inside a sum over here. So minus k Boltzmann sum over I is small variation fi log of fi. Now, a variation, it's like taking a derivative in some sense. So we have minus k Boltzmann sum over I, and here we have a multiplication of two functions. So this is delta fi log over fi plus d log over fi of dfi delta fi.
Times fi.
Why? Oh, okay, yep. Thanks. fi from here. Yes. Okay, so this log of fi stays the same. This is 1 over fi. So fi, 1 over fi cancels out. So we have delta s equals minus k Boltzmann sum over I log of fi delta fi plus delta fi. We can take everything out. By everything I mean delta fi. So we have minus k Boltzmann sum over I log of fi plus 1 delta fi. Alright, so usually what's the next step? You say that it has to be 0. So if it has to be 0, usually what we do that everything is 0, right? So we can say that log over fi plus 1 equals 0. This is wrong. Why it's wrong? Because there is a constraint. What is the constraint? Sum over fi I equals 1. What we do when we try to find a minima or a maxima with a constraint, we use Lagrange multipliers, right? This is why you studied also the first year. Lagrange multipliers. Don't be so excited. It's very easy.
It's very exciting.
Okay. It's not. So what I mean by Lagrange multiplier? So I have to delta s minus, right, minus lambda 1 delta of the constraint. What is my constraint? Sum or I fi, okay, equals 0. That's it. Okay. So if I don't know, or I need to find a minima and maxima, and I find and I have a constraint, so I need to find a minima of a maxima of a function with minus a Lagrange multiplier, which is a constant. I have to find it, multiplied by the derivation or derivative. In our case, is the variation of the constraint. Okay. So what happens here? What we have is, let's put instead of delta s, we put all of those guys. Let's do this as minus lambda 1 multiplied by k Boltzmann. Why? Because I want to take the k Boltzmann as a common multiplier out. It doesn't really matter. Still lambda 1 stays a general thing. So what I have minus k Boltzmann sum over I log of fi plus 1 delta fi minus lambda 1 and k Boltzmann And I have here a sum over I, delta fi, and all of this equals 0. Because the derivative of fi with respect to fi is 1, so I only have the delta fi. Let's put everything inside one big sum. So we have minus k Boltzmann, sum over I, log of fi plus 1 plus lambda 1, delta fi equals 0. Now, the magic of the Lagrange multipliers is that after you introduce them, all the different coordinates, and what are our coordinates, the fi's, are independent. Okay? So if all the different coordinates are independent and all the different delta fi's are completely independent, this sum is 0 only when all the different summands are equal exactly to 0. So we have log of fi plus 1 plus lambda 1 equals 0. So log of fi equals to minus 1 minus lambda 1, or fi equals to e to the power minus 1 plus lambda 1. So all the different i's for all I. So all the different fi's are exactly the same. So what kind of ensemble, the answer was already stated, what kind of ensemble we have where all the different probabilities are exactly the same? It's microcanonical ensemble. In microcanonical ensemble, right, we only care about the number of states because each and one of those states have exactly the same probability. The same goes over here. Okay? All the probabilities are equal to a constant. Lambda 1 is a constant. What exactly is lambda 1? We know that sum over I, fi equals 1. Okay? So we have a sum e to the minus 1 plus lambda 1 equals 1. As e minus 1 plus lambda 1, sum over I, 1 equals 1. This is omega, number of states. Okay. So e to the power minus 1 plus lambda 1 equals to 1 over omega. Okay, and fi equals to 1 over omega, microcanonical ensemble. And the stats is really boring. You promised us something very general, very cute. Okay, you promised us a general principle. We applied this general principle and we obtained a microcanonical ensemble. Okay, this is boring, right? We don't need any of this fancy Lagrange multipliers. We don't need this fancy form of entropy or maximal entropy principle to know that for microcanonical ensemble, all the different states are equally probable. And say to you, yes, you are right. Absolutely right. But remember what we have done when we developed the canonical ensemble. We assumed something. So for the microcanonical ensemble, we do not assume anything. If there are no assumptions, no constraints, what we obtain from the maximal entropy principle, that the entropy will spread around, or the energy will spread around equally probable along all the different states, and this is the entropy where, and each probability is going to be exactly equal to all the other probabilities. So we need some additional physical assumptions, constraints, in order to develop different ensembles, right? So we need an input, a physical input about our system. Remember, what was the physical input when we developed canonical ensemble? We assumed something. Constant temperature. Okay. So I'm not going to use this, but I'm going to assume something that is an outcome of this constant temperature. So we're going to use additional assumptions. And what is my additional assumption is that sum of I, EI, if I have different energies, in canonical ensemble I have different energies. Sum of I, EI, FI equals to U. Okay, so I have a constant temperature. It's basically almost the same as saying I have a different or very specific average energy. Okay. So now, what are equations if we have this? So in this case, this is an additional constraint. Okay. We have delta S equals 0. It has to be always satisfied. We also have delta, or the constraint that sum over I, Fi equals 1. And we now have an additional constraint that sum over I, Fi, Ei equals U. So, if previously for the case of microcanonical ensemble we used only one constraint, now we have to use two constraints. So what are our constraints? So first of all, delta S equals to minus K Boltzmann sigma over I log of Fi plus 1 delta Fi. Now we have delta sum over I Fi, which is the variation of this constraint. It is simply a sum over I delta Fi. And we have an additional constraint. It's coming from this equation, from the average energy, which is delta of sum over I Fi Ei. Now, it's important to notice the energies are constant. I'm not varying the system itself. I'm only varying the different probabilities. Okay? The system is a given system with given specific energies. I want to find the probabilities, and those are my variables, and not the different EIs. Now, the variation of this guy is, again, a sum over I, delta Fi, Ei. Okay, now let's put everything together as we did for the microcanonical ensemble. So we have delta S minus lambda 1 K Boltzmann delta Fi minus lambda 2 K Boltzmann delta sum over I Fi Ei equals 0. So this is my equation. For this equation, all the different delta Fi's are independent. Okay. So I write down everything from scratch. So I have minus K Boltzmann, sum over I, a log of Fi, plus 1, delta Fi, minus lambda 1, K Boltzmann, sum over I, what I have, it's coming from here, so it's delta Fi, minus lambda 2, K Boltzmann, sum over I, Ei, delta Fi. All of this equals 0. We can form one big sum over different AIs and take delta Fi as a common multiplier. So we have minus K Boltzmann, sum over I, log of Fi, plus 1, plus lambda 1, plus lambda 2 Ei, delta Fi equals 0. All the different Fi's, shut up. All the different Fi's are independent. Okay? If they are independent, the sum equals to 0 only when the summands are equal to 0. So we have log for any I, log of Fi, plus 1, plus lambda 1, plus lambda 2, Ei equals 0. Okay. So Fi, or log of Fi, equals to minus 1 plus lambda 1 minus lambda 2 Ei, and Fi equals e to the power minus 1 plus lambda 1 minus lambda 2 ei. This is the probability, and you see, as we expect for canonical ensemble, it somehow depends on the ei. But we need a way to determine lambda 1 and lambda 2, because they are just Lagrange multipliers, they have some constant. What are the ways to find out what those constants are? Exactly. We need to use this constraint. But where we put it? How we use it? I say let's use it for the entropy itself. So what is entropy? Entropy is minus k Boltzmann, sum over I, fi, log of fi. Now, it's minus k Boltzmann, sum over I, fi, and here I'm going to put this log of fi, which is minus 1 lambda 1 minus lambda 2 ei. And it will be clear in a second why I'm substituting for fi something over here, but not over there. So it is minus 1 plus lambda 1 minus lambda 2 ei. Okay, so I have minus k Boltzmann, sum over fi multiplied by 1 plus lambda 1, and I have plus over here, and I have plus k Boltzmann, lambda 2, sum over I, fi, ei. Now, this one is this constraint, okay, and this one is this constraint. Okay, so we obtain that S equals to k Boltzmann multiplied by 1, multiplied by 1 plus lambda 1, plus k Boltzmann, lambda 2, multiplied by u. Is this good? This is bad? I need somehow to determine my different lambdas. Now,
Delta is 0.
yes, but I want, instead of different lambda 2s and lambda 1s, I want physical quantities. Physical quantities. So remember, it's canonical ensemble somehow, so I need temperature.
So
Temperature is a physical quantity.
S to the V.
TU.
dUs to du, ds to du equals to 1 over t. 1 over t. Okay, so we take the derivative of s. This is a constant, we don't care about it. And here is u, so we have 1 over t equals to k Boltzmann lambda 2. Or lambda 2 equals 1 over k Boltzmann t equals to beta. Okay, so we have this guy, lambda 2, check. All right.
אתה לא עושה את ההפוך, כאילו אתה אמור באמצעות זה להגיד את ה-ds ל-du שווה ל-1 חלקי t.
Am I doing it the other way around? What do we mean by other way around? So this is an expression. I have two unknowns, lambda 1 and lambda 2. Okay. Now I want to describe those by some physical constraints, physical terms. Okay. I know something about the temperature. So the moment that lambda 2 is constant, instead of writing something about lambda 2, I'm saying lambda 2, instead of lambda 2, I'm going to write a physical quantity which I call temperature. Right?
נגדיר את זה ואז נמשיך הלאה לטוב.
Yeah. So I'm introducing, instead of constants that I don't really know what they are, and I want to use physical quantities instead of those constants.
ואז בסוף אתה מקבל את החוקים התרמודינמיים.
Yeah, you'll see in a second. Okay, so what do we have? Look on this. So S equals to k Boltzmann 1 plus lambda 1 plus K Boltzmann lambda 2. So lambda 2 is 1 over K Boltzmann, and here we have T. T and U. So Ts equals to K Boltzmann 1 plus lambda 1 Tk Boltzmann plus U. So we have minus Tk Boltzmann 1 plus lambda 1 equals to U minus Ts. And this is? Yeah. This is F. Helmholtz free energy. Alright, so where are we now standing? Fi equals to e to the power this one. Minus 1 plus lambda 1 multiplied by e to the power minus lambda 2 ei. Now lambda 2 is beta. So we have e to the power minus beta ei. Fi equals to, now 1 plus lambda 1 according to this guy is minus beta F. Yep? E. So we got this thermodynamical equations and all the microscopical descriptions that we started from in the canonical ensemble. But how we develop them in canonical ensemble? We used a lot of different assumptions. We derived something, we and expanded in a Taylor series, used the constancy of temperature, etc., etc., etc. And eventually we got exactly the same equation, okay? Which we wrote down as Fi equals to 1 over Z e to the power minus beta Ei, and Z equals minus 1 over beta, oh I'm sorry, F equals minus 1 over beta log of F. Okay. Z. This is canonical description, canonical ensemble. Yeah. Description. Great, so we now proven again, maybe for only 2 examples, that we can start with the form of entropy. We use the maximal entropy principle, and when we obtain the exact equation that describe the probabilities of this specific setting, here canonical ensemble, previously microcanonical ensemble, and we also have the connection to thermodynamics. This is microscopical description, this is macroscopical description. Z is a sum over I e to the power minus beta ei. Right. We only need to know what the probabilities are, what the energies are, and immediately we have a connection to the free energy. Okay. So now that we have this tool at hand, we can design, develop, obtain any ensemble that you want. Any possible ensemble that you can imagine is derivable by using this tool. The only thing that you need is the form of the entropy. You need to find its maximal value, and you need to introduce physical assumptions. Remember, if you don't introduce anything, you'll get a micro-canonical ensemble. If you introduce something about the energy, the average energy, you obtain the canonical ensemble. Okay? So the next step is going to do what? What we are going to introduce. So remember, canonical ensemble was that we have a system, this was our system, and it could exchange energy with the environment. Okay? Microcanonical, the system was closed. Canonical, system could exchange energy with the environment. Okay? Energy. What about the number of particles? The number of particles was constant. But, you know, if you look on any system, the number of particles is not conserved. You always have particles that are introduced that are coming from the outside and particles that are escaping the system. Okay? So most of the system that we are looking on around us are systems that exchange not only energy with the environment, but also particles. Right. So the next step is to develop an ensemble that we can use where the system can exchange energy with the environment and particles with the environment. Why do we need that? Because, well, this is how physics works. We look around us, we see exchange of particles, we need to include it and develop a tool that will address those problems. Okay. So how do we start? We know that S equals minus K Boltzmann, sum over I, Fi, log of I. We know that delta S equals 0. We have constraints. What are our constraints? Sum over I, Fi equals 1. The first constraint. The second constraint, because there is an exchange of energy, I do assume, because I'm in equilibrium, that my average energy is something, and this something I call U. So sum over I, Fi, Ei equals U. And I have another constraint. I do exchange particles with the system, but in order to be in equilibrium, the average number of particles in my system has to be constant. If the number of particles inside my system is not constant, I have a flow, and this means that I'm not in equilibrium. In equilibrium, on average, on average, the intensive and extensive parts or a description of my variables, of my system are kept constant. So I sum over I, Fi, and I equals N. Average number of particles. Yes, you had a question.
Yeah, and if we are exchanging particles, it seems also reasonable that the temperature stays constant, right? Because we assume that the particles may have the same motion.
So you will see that this constant average energy means constant temperature, because it's about exchange of heat. So in order to be in equilibrium, the heat that goes to the heat bath and back to our system has to be exactly the same, so the temperature has to be constant. The same goes about the average number of particles. So if on average the amount of particles that are getting in equals to the average number of particles that are getting out, the total number of particles is conserved. It's always about conserving in the whole large system everything. Okay? So the exchange have to cancel each other. If it cancel each other, then the average energy is kept constant and the average number of particles kept constant. So you can now guess. For the canonical ensemble, we got a constant T, right? So this was the physical parameter that we introduced. If we have a constant average number of particles, what is the parameter that we are going to introduce?
Chemical potential.
Chemical potential. All right, now let's start with this variation business. I can agree the variations are a little bit boring. You're not excited anymore.
And it's going to be the same.
It's going to be exactly the same, yes. So we have delta S equals to minus K Boltzmann, sum over I, log of Fi, plus 1, delta Fi. We have delta of sum of I, Fi, it equals to sum over I, delta Fi. We have the constraint delta of sum over I, Fi, Ei. It is a sum over I, Ei, delta Fi. We have delta of sum over I, Fi, Ni. It is a sum over I, Ni, delta Fi. Great. Now let's put everything together. So we have delta S minus lambda 1 K Boltzmann delta sum over I Fi minus lambda 2 K Boltzmann delta sum over I Ei Fi minus lambda 3 K Boltzmann delta sum over I Fi Ni. All of this equals 0. So Ni, remember, those are the different number of particles for each state, and these numbers are constant, exactly as the energies for each state are constant. Now, we put all this together exactly in the same fashion as we did it for microcanonical and canonical inside. So it turns out that we have minus k Boltzmann sum over I, and here we have log of fi, we have plus 1, we have minus lambda 1, we have minus lambda 2 ei, and we have minus lambda 3 ni, delta fi equals 0. Now again, the moment we introduce the Lagrange multipliers, if we have this summation and it equals to 0, we assume that all the different fi's are independent. This means that the summands must be 0, and the summands are 0 either when delta fi's are 0, which is not true, or when those terms are 0. So we have log of fi plus 1 minus lambda 1 minus lambda 2 ei minus lambda 3 ni equals to 0. Log of fi equals to minus 1 plus lambda 1 plus lambda 2 ei plus lambda 3 ni. Okay. And fi equals to e to the power minus 1 plus lambda 1 multiplied by e to the lambda 2 ei multiplied by e to the lambda 3 ni. Now we have to determine what are the different constants, lambda 1, lambda 2, lambda 3, or at least describe them in terms of some physical quantities. So we're going to use our constraints. What are the constraints? Sigma of I fi equals 1, sigma of I fi ui equals u, and sigma of I fi ni equals 2n. What quantity we use in order to introduce the constraints? Again, the entropy itself. S equals minus k Boltzmann, sum over I, fi log over fi. So S, it's minus k Boltzmann, sum over I, fi, and here I have log of fi. Log of fi is this guy. So it is minus 1 plus lambda 1 plus lambda 2 ei plus lambda 3 ni. Okay. So S equals to minus k Boltzmann, sum over I fi plus 1 plus lambda 1. This is the first constraint because sum of I fi is going to be equal to 1. 1 plus lambda 1 is a constant getting out of the sum. We have minus k Boltzmann, lambda 2, sum over I fi ei. This is the second constraint, and this quantity is going to be equal to u. And we have minus k Boltzmann, lambda 3, sum over I fi and I, and this is n.
But shouldn't it be minus lambda 1?
So it is 1 minus lambda 1. 1 minus lambda 1, thank you. And minus lambda 1, thanks.
Two lines back to the in the second,
Two lines back to the
third row.
This.
Yeah.
Yeah. Thanks. Alright, so this is 1, this is u, this is n. Okay, so let's see what we've got. We obtain that S equals k Boltzmann, 1 1 minus lambda 1 minus k Boltzmann lambda 2 u minus k Boltzmann lambda 3 n. Yes.
I think didn't you have a plus behind the lambda 2 in the canonical expression? Because now lambda 2 is minus beta, so it's okay.
I think it should be fine. We'll find in a second if it's not going to be equals to beta.
Beta, not beta.
We'll see in a second. We'll see in a second. Hopefully.
On your horses.
Yeah. We'll see in a second. It's look, if we are not going to get something like a microcanonical ensemble or canonical ensemble, we will know that I made a mistake. All right. So what do we have over here? So we know again that ds to du equals to 1 over t. So what we have is minus k Boltzmann lambda 2 equals to 1 over t. Lambda 2 equals to 1 over k Boltzmann t minus 1 over beta.
No,
Beta. Beta. Now I already see that this is fine. Why it's fine? Because I have here lambda 2 ei. So instead of lambda 2 I'm going to have minus beta ei. Then it's fine. Great. Okay, so we write it down now in terms of beta. So what we have, S equals to k Boltzmann, 1 minus lambda 1, minus k Boltzmann, plus k Boltzmann beta, right? U minus k Boltzmann, lambda 3, n. Okay, so I want to now get out u out of this equation. Why I want to get out u? Because I need to know something about lambda 3. And I know that du to dn equals to mu. This is the chemical potential. Remember, so E related to T. Average energy related to temperature. Number of particles related to chemical potential.
Can't you do ds to the n mu?
No, I want this. I don't remember a lot of mathematical formulas related to thermodynamics. I know 3 or 4 by heart, and I want to use them. Okay? There's a lot of thermodynamical formulas. I don't know 95% of them. So do you. They're written somewhere in some dusty book. All right. So what we have? We have here k Boltzmann. So we have. Let's figure this out. Let's divide everything by k Boltzmann. So this term is simply 1 over t, right? This term is simply 1 over t. So we have Ts equals to T k Boltzmann, 1 minus lambda 1, plus U minus k Boltzmann T lambda 3 n. Great. So now U equals to Ts minus T k Boltzmann, 1 minus lambda 1 plus k Boltzmann T lambda 3 n. So du to dn, it equals to mu, and it equals to k Boltzmann T lambda 3. So we have lambda 3 equals to mu beta. Right? So it's mu divided by k Boltzmann T, and 1 over k Boltzmann T is beta. Okay, so the two parts is this, we have this, and the only part that we have left with is what is 1 minus lambda 1. We don't really care about lambda 1 itself because it's always appearing as 1 minus lambda 1 in the probabilities.
Just a normalizer.
Yep. Oh no, it's not just a normalizer. It's the thermodynamical potential that is the potential of this ensemble.
No, lambda 1.
1 minus lambda 1.
Yeah, that's the normal.
So what we got, I will discuss it in a second. You will see. Great. So let's put everything back inside. We have U equals to Ts minus T K Boltzmann 1 minus lambda 1 plus K Boltzmann T lambda 3 which is mu n. U minus Ts minus mu n equals to minus T K Boltzmann 1 minus lambda 1.
That's the Gibbs.
What is this?
Gibbs energy.
This is the Gibbs free energy. Okay, so let's call it G, oh no, psi, which is this psi. It equals to minus T K Boltzmann 1 minus lambda 1. And we are getting that 1 minus lambda 1 equals to minus psi 1 over, no, beta.
I think that the ground potential is in the Gibbs field. The Gibbs free energy is right?
It's P or minus mu n. So it's called grand canonical potential, but it's also the Gibbs free energy. Okay? So remember, all the different thermodynamical potentials are Legendre transformation from the energy. Okay? So what is the transformation? You have U, which was in which coordinates? In S and in N. When I performed this Legendre transformation, this grand canonical potential or Gibbs free energy is now in what coordinates? In T and in mu. That's it. Okay? So remember when I told you, well, if I want to act in those coordinates or in those coordinates, intensive, extensive, it's not only related to the matter of choice, it's also related what describes my system. The free energy describes a system that is acting according to canonical potential. The Gibbs free energy describes a system that acts according to grand canonical potential when I can exchange energy and particles. So this has a name, grand canonical potential. All right, let's bring everything back together. And let's see what we have. So first of all, this is the probabilities. We can introduce Fi equals to E lambda 2 Ei, which is e to the power minus beta Ei, lambda 3 Ni. What is lambda 3 Ni? What is lambda 3? Mu beta plus mu beta Ni. And here we have e to the power 1 minus lambda 1. It's e minus beta psi. So e to the power beta psi. Okay. Now, I can write it down in slightly more common way. So Fi equals 1 over z e to the power minus beta Ei minus mu Ni. Z is going to be a sum over I e to the power minus beta Ei minus mu Ni. So it's a normalization constant, but it's also related to the grand canonical potential, to the Gibbs. So we have psi is 1 over beta minus log of z. So all of those are the equations for the microscopical probabilities of what we call a grand canonical ensemble. Now, a very interesting point to notice. So you mentioned that, well, 1 over this 1 minus 1 to 1 is just a constant. It's a normalization constant. And you're right. It is a normalization constant because it's basically gives us 1 over the partition function, right? But it's also the constant that relates to the thermodynamical quantities. If we want to compute anything, pressure, volume, temperature, not temperature, average energy, anything, we have to go through this normalization constant, which is the potential, the thermodynamical potential that we have. Now, we will stop here, and in the next lecture we will see the examples that are related to quantum gases. You'll also see them during the TA. The thing to notice is that, well, we have derived, using this tool of maximal entropy, 3 different ensembles. But the same thing can happen to any other. So if you have a question, like 2 years ago in an exam, to derive an ensemble for specific where the system can exchange pressure with the other system, this is the way to go. There's not a lot of questions that I can ask about different properties of the maximal entropy. But this derivation and how we use it, it's an important issue. Okay, see you all on Tuesday.
שבסעיף האחרון, מה שבסוף מבקשים, זה בטמפרטורה גבוהה.